CNT140, we're on Chapter 9. We're continuing on with our cable testing. We're now kind of the performance area of our cable testing. So we're looking at things like impedance, resistance, return loss, that sort of thing. What we have to remember about impedance is going to change with frequency. And impedance is your total opposition to current flow. Hopefully you remember that from before. And again, I threw this out here just so you could recognize, you don't need to know the math, but just so you recognize that it is a factor of frequency. My impedance is actually a calculation involving reactances, and frequency is a part of that. So, as the frequency of our signal increases, to add more bandwidth, the impedance of the cable is going to change. That's why the structure of our cabling, category 5, 6, 6A, 7, blah, keeps changing to make sure that we keep our system at 100 ohms impedance. If we look at our standard, it says our twisted pair cabling should be 100 ohms. It should be balanced 100 ohms cabling. So that needs to remain consistent. Well, over the years, we've had things like category 3 cabling. As we wanted to add more bandwidth to our system, we increased the frequency. So therefore, the structure of the cabling changes to keep it at 100 ohms. Increase the frequency, more bandwidth. Structure of the cabling changes to keep it at 100 ohms. Add more frequency, get more bandwidth. Structure of the cabling changes to keep it at 100 ohms. Increase the frequency, add more bandwidth, structure of the cabling changes to keep it at 100 ohms, and so forth. And so far, that has been pretty much the trend as we go from category to category to category to category. And that is to try to keep it at 100 ohms impedance. And the idea behind that is, if I keep it consistent, it's going to equal basically maximum signal transfer. If it does not remain consistent, you're going to have reflected signals, and you're going to have signal loss and errors, if you will. Okay, you're going to have signal reflections. So it's important to keep our whole system at 100 ohms impedance, and the easiest way to do this is to make sure all the components are the same category. So therefore, everything is the same impedance and maximum power transfer. And that is the whole patch panel, cabling, outlet jacks, patch cables, the whole 9 yards. Make sure everything is the same category, everything is therefore the same impedance, maximum power transfer. Okay? Alright, so a follow-up to impedance is return loss, structural return loss. Structural return loss is the reflections caused by the variations of impedance. So again, if I keep all my components category 6, I'm doing as much as I can. If I get any structural return loss now, it's going to be due to the manufacture of those components. That's what it's really going to be down to at this point. So, according to my standard, there is a return loss value of what's acceptable, what's not, and there's actually in the standard you can find that it lists what they are. And what'll happen is after I hook up, after I cable my system, everything category 6, and I've done as much as I can to make sure all the components are the same category, I've terminated things well, I put a performance meter on one of these certification meters, and you'll notice it looks like it's 2 meters. Well, it's actually just a meter with 2 parts. We have basically the main end and the remote end. It gets hooked up to your cable run like so. Maybe I put the main end here in where the patch panel is, through my horizontal cabling out to an outlet, and I put the remote end out here. This is going to run a battery of tests across this link and back and indicate to you, do you have acceptable levels of return loss, or do you have too much return loss because of variations in impedance across your cable system. And if you do, and actually when you test, it does a whole battery of tests, and one of these will be your return loss test, and it's looking to make sure it's in that acceptable level according to the standard. As long as it is, it's going to report that everything's okay and it's good. But if I have too much variation in impedance across my components or my cabling, it might have too much return loss, therefore the link would fail. In that case, now I'm down to maybe the quality of components I'm using is pretty lousy. Maybe I have mismatched different brands. Maybe I have bought the bargain bin cable, if you will, and the production of it is not very good, and I'm getting a lot of structural return loss. So there's your first level of performance test, okay? And that is one of those, only the performance meter can do this to test for that return loss. The next thing they mention is cable length. The cable length of our cable run can be tested with what's called a time domain reflectometer, TDR. This works on the same idea as like a radar. It knows electricity travels through a link at blah meters per second, and it'll send a pulse out, wait for it to get to the other end and bounce back, and it's like, well, you've been gone X number of milliseconds, so therefore I know the cable run is blah feet long or blah meters long. And little guys like this guy can do distance measurements. Little guys like this, like we have, can do distance measurements. And it's important to make sure that those distances are below the 100-meter length. And after I install a cable run, I test the length of the cable run, again, making sure it's below 100 meters. But also then after I do that, indicate or mark what the distance is. If I install it today and it's a 70-meter cable run, I document that for troubleshooting later. I come back later and it comes up a 40-meter cable run, I know I have a problem and I know approximately where it's going to be. So that is valuable. And if I look at the specs of a TDR, they usually tell me how accurate they are. In this case, that little TDR meter we were looking at is accurate to within about a plus or minus a foot. Well, even if it's plus or minus a meter, that's going to get you in the right ballpark of where I'm looking for my problem. Really valuable. The next performance level problem they talk about is attenuation. This is your loss of signal over distance, over the length of the cable, measured in decibels. Okay. Hopefully you remember attenuation. Yeah, loss your signal over distance, measured in decibels. Hopefully you remember we actually call this more properly insertion loss. Insertion loss is the more modern term. Again, the measure of the decrease of signal as it travels down the length of the cable. The standard has a limit on amount of insertion loss that's allowed, and again my certification meters are going to test for that and make sure it's in acceptable levels. I hook it up on each end of my cable run the battery tests, it'll come back with blah, here is my attenuation level for the link. So as long as it's not too great, this cable run is perfectly usable. Again, another performance level criteria and test that's done with our certification meter. The next performance level thing that we look at is crosstalk. Crosstalk, hopefully you remember, is the signal jumping from one wire pair to another one, the unwanted signal jumping from one wire pair to the other one. And the main cause of this is my poor terminations. Too much wire untwist, allowing that signal to jump from one wire pair to the next. So, near end crosstalk is just that. It's happening at the near end of my cable. Far end would be happening at the far end of my cable. So, if I'm looking at the end here where the patch panel is, if I have sloppy terminations here, the signal could be jumping from the orange pair over here to a green pair on this end. If this is the outlet jack over here, it could be occurring over here because, again, sloppy terminations at the outlet jack. So, our standard gives us a level of acceptable near and crosstalk values. And again, as I hook up my meter, it's going to do a test. And when it tests, it's going to give me a result that looks something like this. So this is one time I've zoomed in a little chart so you can see what's going on. It's actually looking for the signal to be nice and strong. If it drops below this little level here, it's saying that the signal has crosstalked too much and therefore has fallen below the limit. So I put down here a number of a high decibel number indicates a strong signal with little crosstalk. A low decibel number is indicating a weak signal where a bunch of that has crosstalked and jumped to another wire pair. So I'm looking for this actually to be a nice strong number above the pass-fail line. That's something that we'll need to keep an eye on. The main cause of crosstalk is just that, poor terminations. Too much wire untwist at patch panel, outlet jack, patch cables. That's what's going to cause that. So I'm looking out for this ½ inch of untwist that's allowed at each termination point. Minimize that, keep it nice and tight in my terminations. Don't allow the wires to be nice and long here and have lots of untwist. Don't allow the wires to be nice and long here and have untwist. Again, these are all examples of what not to do. Here's another one with a bunch of untwist. When I go to test this, my little continuity meter cannot pick this up. This is just a little wire map. It's like, okay, I see that I have cabling connected. My little wire mapping tool, same thing. I see that my cabling is connected. It's not until I get to my performance meter is it actually going to pick this up and go, whoa, you got too much untwist, so therefore you have crosstalk issues. The crosstalk failure is alerting you to the fact that you have too much untwist at your points of termination. Along with this is a more modern measurement of crosstalk, alien crosstalk. As we get to high levels of frequency, I can have coupling from pair to pair on adjacent cables. So I can have literally the blue pair here cross-talking to a blue pair over here. Because again, those wires are twisted at the same twist pitch between those cables. So I could actually have a signal over here be cross-talking to a cable over here. In that case, what actually has to be done is the signal needs to be sent on multiple cables and measure on another cable to see if there is crosstalk. That's a very tedious test to do, but that's what alien crosstalk is when you're looking at crosstalking between different cables. One of the next measurements they talk about is the attenuation to crosstalk ratio. This is trying to give you a value of kind of like how good is this link? How good is this link? And here again, your standard gives you a level of attenuation to crosstalk ratio. Again, my performance meter is going to be hooked up and test for this. Give you, it's going to test for the acceptable levels. Hook it up like so, and I'm going to, after I do my test, look at the ACR level. Now, this is kind of a measurement of, all right, has the signal, I don't think I put, yeah, actually I did put it here. Has the signal attenuated more than there is noise? Okay, so this as I take a look at back here again, attenuation to crosstalk ratio. So it's looking at, all right, if the signal has not attenuated too much, it should be good and strong. The crosstalk is going to be weaker than it. However, if my cable is going a very long distance and is terminated very sloppily, the signal is going to attenuate and the crosstalk is going to overwhelm it. So this measurement is kind of that, all right, is the link of good quality with all factors, kind of factored in. The attenuation of the signal as well as the crosstalk. So this is kind of a real quick check on kind of the overall quality of this link after it's been installed. So a lot of people pay attention to the ACR measurement. One of the last ones they talk about is propagation delay. How long does it take the signal to propagate from one end of the cable to the other one? Well, electricity through a copper cable is a known value. It takes blah nanoseconds to get across so many feet of cabling. Well, that actually gets used in calculating distances of the cable. And here gives you, again, the standard has limits on how much propagation delay is allowed per frequency, if you will. Okay, and again, your meter is going to check for that. It's going to test for that and make sure that it's not too great. Skew then is also, or I should say skew is kind of like in the same field as propagation delay. As I send a signal down blue, green, orange, and brown pairs, because they're twisted at different mounts, they're going to arrive at the end at slightly different times. So as long as it's not too great between them, it's okay. But if it is too great between them, I'm going to have what's called skew, meaning, in this example here, the signal got to the brown end of the cable much quicker than it did the blue cable. And now we have things out of alignment or jittered, if you will. Some data is arriving in one pair before the other one. Too great of a difference between them. And again, standard gives us a allowable limit on the amount of delay skew that you can have on your cable runs. Again, your meter is going to check for that. Your certification meter is going to check for that. All right. One of the last things they mention is the whole certification versus verification. Verification is just that. Am I able to get a signal across? Certification is what performance level am I getting across this cable? And that's where your certification meter comes in. One last little thing I'm going to mention in this chapter is if you're trying to locate a cable in a bundle. If I have a bundle of cables and I'm trying to locate a specific cable for troubleshooting purposes, that can be done with a toner probe or what's called a fox and the hound. And here's two examples of those. You have one end that's the sending unit, this guy right here, this guy right here. This you hook up to your cable run and it's going to emit a little electronic warble into the cable. The probe here, okay, the probe here, the wand if you will lay next to the cable. So I hook my little toner up here and that's going to connect into the wire and going to emit a little electronic warble in. The probe will, as I move it past my little wires in there, will pick up that electronic warble when I have found the correct cable. So it's going to allow me to find a cable out of a bundle if I need to troubleshoot. Very handy to do. We'll do that in lab. And that's the end of Chapter 9.